So right now I want to talk about transformations of a function. So if I have a function f of x, what sort of things act on it? What does the a do? What does the h or the k do? So first thing to note, the y equals, this is the output, right? The dependent variable. So what does a do? What effect does a have on the graph, the f of x graph? So when it's outside, it's being multiplied by f of x. It's a vertical stretch or compress. So it stretches the f of x function, so it multiplies the y's by a. Okay, so it stretches it if a is bigger than 1, but it compresses it if a is between 0 and 1. Now, if a is negative, so if a is less than 0, it's first a reflection. So a negative a will first reflect over the x-axis. It's again a vertical change, so it's a vertical reflection. So it's reflecting over the x-axis. And then the same thing goes for a. Ignore the negative, and then if it's a number bigger than 1, it's a vertical stretch, and a compress if it's between 0 and 1. So f of x, like I said, is the function. It's the original function will be given by a formula. So this h is inside the formula, the k is outside the formula, this a would be multiplied outside the formula. So f of x is just the function and its independent variable, which in this case is x, right? Y is a function of x, or f is a function of x. So what does h do? So it shifts the graph right and left. Notice h, it says minus h. So we shift the graph left when h is less than 0, right? So if h is less than 0, it means it's a negative. So we'll see a minus a negative number. In other words, what we'll see is we'll see x plus some given number, okay? So a plus sign is going to mean shift it left, whereas a negative sign is going to mean shift it right. And the k is the vertical shift, up, down. Shift the graph up when k is bigger than 0, down when k is negative, less than 0. All right, and how do we combine these shifts? Well, the right and left shifts are independent of the up and down shifts. So you could do h first and then k, or k then h. But when we do compressions combined, so here we have a vertical compression and a shift, what you should do is do the compression first, or stretch. So do the vertical stretch or compress and then move it. Right? This is a rigid transformation. This one's a non-rigid transformation. Right? So this and then this. If there were a b in here in front of x, so you do bx and then minus h, so actually you'd shift it. And then multiply all of the x values by 1 over b. So it's kind of opposite. So let's look at a specific example to help. Otherwise, this can be kind of confusing. So let's look at the function, the parent function, f of x equals x squared. Now, graphing this out, I have a point at 0, 0. 1/2 would be at like 1/4, and negative 1/2 would be also at 1/4. At 1, 1 squared is 1, so let me make a table of values. X and then f at x. Right? So let's start at, this is negative 1, 2, 3, 4. Let's start at negative 4. At negative 4, I have negative 4 squared, which is 16. Negative 3, I would have negative 3 squared, which would be 9. 1, 2, 5, 6, 7, 8, 9. So right here. At negative 2, I have 4 because I'm squaring the values, right? 1, 2, 3, 4, right? At -1, I have 1. At -1/2, I would have 1/4, right? That's someplace down there. So it's really small here and fat, and then it grows really, really fast at the sides, all right? And then the same goes here, 1, 1, 2, 4, 3, 9, 4, 16, etc. All right, something like that is what the graph looks like. So 1, 2, 3, 4. And I sort of missed my marks here. Let me try to clean it up a bit. All right, something like that. This is an even function because it's symmetric. That's right here. Okay, it's an even function because it's symmetric on the y-axis. That's what an even function is. All right, so now let's look at some transformations of this function. First of all, let's look at up-down shifts. So here's what it would look like. F of x equals x squared plus, say, 3, right? So what I'm doing is I'm taking all of the y values and adding 3 to it. So a table of values, I should maybe call this g of x. Let's call this g of x. So then g of x is now f of x plus 3. Okay, so it shifts the f of x graph by 3. So when x is -4, then instead of 16, I have 19. -3, I have 12. -2, I have 7. At -1, it's 4. At 0, instead of being 0, 0, I have 0 and 3. So what this does is it takes every value and shifts it up 3 units. So 0, 0 shifts up 1, 2, 3 to be at 0, 3. This 1, 1 shifts up 1, 2, 3, okay, to be at 1, 4 and -1, 4. This value, 1, 2, 3, right? So it should be 2, 7, which we see, and -2, 7. Right, so this 1, 2, 3 would be up here. So 1, 2, 3, up here. So the graph has the same shape. I'm missing my points here. The graph has the same shape. It's just shifted up 3 units, right? I made it quite messy because I graphed this point 1, 2, 3 incorrectly. All right. So imagine this as a rigid shape. Rigid means hard, so I could pick it up just as it is. So I pick it up and I move it up physically 3 spots. That's how I get that one. If it were -3, it would all shift down 3. Let's look at the left and right shifts next. So if I shift, let's say for instance, if I write h of x equals, what I'm going to write next is f of x minus 3. Okay, the function of x minus 3. So that becomes x minus 3 squared. All right, what does that -3 do? Now I'm changing my x values and leaving my y values alone. So looking at the parent function table, x, y. So I'm going to change x and leave my y alone. So 16 should be do -4 plus 3, okay, because it's inside, it's opposite what we think. -4 plus 3 is 7. So when x is 7, I have 7 minus 3 squared is 4 squared, which is 16. Right? So I'm actually adding 3 to all of the x's. One of my students says it's almost like compensation. So if it has -3, I actually need to increase x by 3. So instead of going through 3, 9, it's going to be 0, 9. Sorry, -3, 9 is 0, 9. Also 3, 9 will also be 0. No, it'll be 6, 9, won't it? So when x is 0, I have 0 minus 3, which is -3. -3 squared is 9. At 4, it used to be -2. Change the x value, add 3, and I get 1. When x is 1, y is 4, because I would have 1 minus 3 squared is 2 squared, -2 squared, which is 4. All right. Now at 1, add 3, I have 2. And then 0, it used to be 0, 0. Now it's 0, 3. All right, so let's look at what this is. I have 0, 3. That 1/4 and -1/2 is now 1/4 and let's see, 1/2 plus 3 is, sorry, -1/2 plus 3 is 2 halves, 2/5, 2.5. All right. Also 3.5. If I were adding 2, 1, we would also see that when I put 4 in here, I would also have 4, 1. Then I have 1, 4, 1, 2, 3, 4. I would also see that I would have 5, 1, 2, 3, 4, 5, 4. Right? And then I have 0, 9. So when x is 0, y is 9. So what I will see is when x is 6, I also have 9. So it's a curve like this. And what you see is I'm taking this parent function in blue and shifting it over every single point over to the right 3. Even though it says x minus 3, I'm actually shifting it to the right 3 units. Right? So the next thing we're going to talk about are the stretch and compresses. So what happens if I write f of x equals 2x squared? 2x squared. All right, now I'm again changing the y values. So it shouldn't be f of x. I should call it y for now. Let's call it t of x, I guess. Right. So what I have is I'm going to leave the x values the same, 4, -4, -3, -2, -1, -1/2, 0. And then it repeats 1/2, 2, 3, 4. So now I'm taking the y values and multiplying them by 2, right? So when I plug 4 into here, negative 4 into here, I have 16 times 2, which is 32. When I plug 3 in here, I have 9 times 2, 18. When I plug a negative 2 in here, I have 4 times 2, 8. This becomes 2. This is 1/4 times 2, which is 1/2. Right? And then at 0, it's 0, 0, so it's 0, 0 still. 0 times 2 is 0. So what I'm seeing is on the graph, when I plug these in, this point stays the same. This point right here, 0, 0, shares a vertex. All right, but instead of going over 1 and up 1, I go over 1 and up 2. Over 1, up 2. At negative 1/2, it's also 1/2. 1/2 and 1/2. Instead of negative 2, 4, I have negative 2, 8. So at 2 and negative 2, it's all the way up here at 8. 2, 8, and negative 2, 8. So what I'm seeing is that I'm stretching this graph out. Imagine taking that parent graph, the one in blue, and just stretching it up a little bit higher. And that's what I have with this green one. I'm going to pause, redraw so that we can, my graph is getting a little bit busy. Okay, so now we see that parent function again. I'm no artist, so it's poorly drawn. Use your imagination. It's called a parabola. So now that vertical stretch, 1, 1, 1/2, 1/2, negative 1/2, 1/2, then we have 1, 2, negative 1, 2, 2, and negative 2 all the way up to 8. So 2. So now you can see the stretch a little bit better. So what you imagine is that it's like a rubber band. It's being held at the vertex and just stretched upward. So what I see is I see an upward stretch. All right, so that is a vertical stretch, but notice it also compressed it horizontally. So let's look at a horizontal compression. Let's look at what happens when I have, I'm going to do g of x again. G of x for this graph is, let's call this 2x squared. All right, 2x squared. Now what I'm doing is I'm changing the x values. So to compensate for the x being doubled, I need to cut my x values in half. So my original function, f of x, what I had was negative 4, 16, negative 3, 9, negative 2, 4, negative 1, 1, 0, 0. But now what I'm going to have is, to get out 16, x only needs to be a 2, because 2 times 2 is 4. 4 squared is 16. So at negative 2, I have 16. Negative 2, 16. At, to get negative 3, it's not a super pretty number. Sorry, to get 9, it's nothing pretty. Let's skip it because it's odd. So what I'm going to do for the 4, it's negative 1, 4. All right, plug negative 1 in here. I have negative 2 squared, which becomes 4. For 1, I would need 1/2, positive or negative, it doesn't matter. And what you'll notice is 0 stays 0. Okay, so what I seeing is I'm actually horizontally compressing. The 2 is horizontally compressing by 1/2. It's vertically stretching, but it's horizontally compressing by 1/2. All right, so we have 0, 0. We have negative 1/2, 1, and positive 1/2, 1. Then we have negative 1, 4, positive 1, 4. Notice that this is compressing it horizontally by a factor of 1/2. And it's causing it to grow vertically by not 2, but notice it's causing it to grow vertically actually by 4. How do I know that? Because g of x is the same thing as 2x times 2x, which is 4x squared. All right? So this horizontal compression of 1/2 is the same thing as a vertical stretch of 4. Right? So then I have, let's see, negative 216 and positive 216. Well, that's way up here, right? So I have a graph that's really, really steep now. Okay, it's been squished in horizontally and pulled vertically. So that means if f of x, if I have a times f of x, that is a vertical stretch by a. But if I have f of bx, that is a horizontal compression by 1 over b. All right? Opposite when it's inside. Just like a negative actually moves it to the right, when I multiply, I'm actually dividing.